Good afternoon. A little better. All right. Welcome to Cloud Storage Considerations for RAG and AI applications. My name is Scott Hoag. I'm a product manager at Microsoft. I work in Azure Object Storage, so both our traditional object storage service and then all the protocols that we layer on top of object storage, including HDFS, NSS, NFS, SFTP, all that good stuff. My colleague Daniel with me today as well. Daniel?
Yeah, my name is Daniel. I'm a product manager working in the team of Scott. I'm responsible for our object SDKs and client tools, like Azure Write, as example, our local emulator for dev and test, and our Swiss Army knife CLI tool, AC Copy. Besides that, I'm working with our largest customer at exabyte scale.
All right, so we'll kind of go ahead and get into things. I know you've seen a lot of repeats of what history looks like here. I actually think it's kind of important to look back at where we came from to see where we are today and potentially where we go towards in the future. We'll do a brief overview of AI workloads and storage requirements from our perspective and from a storage-centric perspective. I think we have some unique insights there given we're the team that supports some of the frontier companies like OpenAI that are doing massive training on our platform today. And then we'll get into talking about RAG on our platform. So where did we all start? If you go back to the late 90s, early 2000s, there was a lot of research at the time. We started to see white papers come out and research studies come out from Berkeley around things like Ocean Store. We had Centera and content addressable storage systems, kind of the early days of thinking about object storage systems. In the early 2000s, then we saw the introduction of Amazon with S3, kind of simple, eventually consistent object storage platforms. We saw Swift, SwiftStack, and Ceph come in at the time. But the primary use case for these platforms at the time was backup, archive, maybe some minimal kind of cloud native apps. We didn't really care about things like latency. It was okay to have time to first byte potentially measured in seconds instead of milliseconds. And we really didn't have performance drivers for object storage to move us forward. We started to see that in the late 2010s, 2015 to 2020-ish timeframe, things like big data started to become more prevalent. We started to see vendors that were doing big data and analytics start to store more and more of their data on object storage platforms like ours, those from Amazon, Google, and others that are out there. And that drove us to do some interesting things. So at Microsoft, that drove us into a place where we developed a hierarchical namespace, which we offered as an additional protocol on top of our traditional REST APIs that existed. And that hierarchical namespace eventually enabled us to bring other protocols on our platform as well. So we can offer customers a single namespace with object storage, and they can come in and do blob storage, or they can do HDFS connectivity, they can do NFS v3, they can do SFTP, all over the same namespace. We also saw some other interesting things come out in this time period. So our storage platform at Microsoft with Azure Blob Storage, we were always a strongly consistent object storage platform from the start. That was a design decision that we made way back in the beginning in 2008, 2009. When we were developing the platform, we saw other vendors like Amazon come over to that strong consistency model as well. And then we're also starting to see these vendors adopt hierarchical namespaces. So we see this across both Google and Amazon and other hyperscalers. Moving beyond kind of those traditional big data customers and what we kind of saw as the earlier days of really large machine learning runs on top of our platform, we saw the introduction of pure play storage vendors. Kind of interesting. We have the Wasabis out there, Backblaze, R2, effectively disaggregated storage that customers can buy into and go ahead and store their objects over there. But we also started to see that other workloads became viable on object storage as we increased the performance on our platform. So, looking back, I joined Microsoft about 5 years ago. I think at the time that I joined, we could drive a single storage account to 60 gigabits a second of ingress, about 120 gigabits a second of egress, and 20,000 IOPS. In 5 years since I've joined, now we run tens of terabits per second ingress and egress, and hundreds of thousands of IOPS on a single exabyte scale namespace. And we kind of continue to see that only going up and up and up, both for our AI training customers, also for those that are doing things like fine-tuning on our platform, and they have more and more needs for more and more performance out of their platforms. So just to give you kind of a quick tour and lay of the land for those that aren't familiar with Azure Blob Storage, yeah, we're not Amazon, we're not S3, we're that other object storage platform out there. So we have a object storage platform that we call Azure Blob, and then on top of that, we layer a bunch of other protocols and capabilities on the platform. So what this lets us do is it lets us take our FNS namespace and then offer clients connectivity over their protocol of choice with multi-protocol access. So we can have a client that can say like an EDI job that only talks SFTP. Great, it can upload its objects over SFTP, and then we can have a Databricks cluster come in and read that over HDFS, do some kind of ETL and transformation, ultimately push those things downstream. So multi-protocol is very unique within our platform. The other thing that we have, and we've had for some time, is an SSD-backed object storage offering. So we have a standard storage offering, and then we also have a premium blob storage offering, which is SSD-backed. Higher IOPS, consistent low latencies, really good for particularly kilobyte-sized objects. So when we're thinking about object storage and having kind of time to first byte that's measured in single-digit milliseconds consistently at P99, you know, we kind of have premium blob and offerings like that out there. We also have traditional block storage, we have file storage services, but we'll kind of focus on object for today. The really cool thing about our platform, and I can't kind of stress it enough, is the MPA capability, or our multi-protocol access. So we layer everything on top of that flat namespace, all the capabilities that we build for that flat namespace, whether it's things like geo-redundancy or zonal resiliency in our platform. It could be a data management feature like leveraging lifecycle management, access tiers, being able to transition your objects between hot, cool, cold, archive, all these things. They're all built on a consistent API surface, and then we layer those protocols on top of them. So as we build new capabilities into our flat namespace, quite often our additional protocols also pick up the niceties, and they get to take advantage of that right from the start. So that could be things like maybe, like I said, a new tiering capability. It could also be a perf and scale aspect in our platform. So as we improve perf and scale on our flat namespace, our customers that are on hierarchical namespace also get to take advantage of all that. So what's it look like in a storage-centric view of the world? If we kind of look end-to-end from being able to do AI training workloads all the way through to fine-tuning and inference, it looks pretty traditional. So if we go back to kind of that big data view of the world, where I need to ingest a bunch of raw data, we need to do some type of transformation or cleansing on top of that. That could be deduping our data, it could be pulling data sets together, it could be running additional detections on top of images or videos or things that are coming in. Eventually we'll be able to do kind of get a clean version of that data for data prep, and then that's passed over to these supercomputers, these AI supercomputers with thousands and thousands of GPUs and all their ephemeral disk and compute and everything that comes with them for training, ultimately to generate checkpoints, which then, once we're done with the training job, we produce a set of model weights and push those out. So the interesting thing about our platform is we see, particularly with our large kind of larger AI training customers, we see checkpoints getting bigger and bigger. So we're often thinking about ways that we can solve that and make that experience better for our customers, not only on the compute side. So how do I take that checkpoint from GPU, push it down and maybe get it over to the CPU side, get it onto ephemeral disk, and ultimately be able to persist checkpoints back to object storage in case we ever do have to rehydrate along the way and restart a training job. There was a question earlier in one of the previous talks about, like, do customers save these checkpoints? Do they pull them down to archive? Sometimes yes, like if they really want to bring them through. Ultimately, like the base model weights at the end of those training jobs are the most important things. But when we do see customers persist checkpoints, they often don't persist all the checkpoints. So you might have a random researcher that's hopping in the middle of a training job, doing some iteration and some experimentation, and they'll generate a series of checkpoints, and they may or may not need those. But quite often along the way, you'll see snapshots as things are going. So not everybody does training of these massive foundational models. We're not all out there running 20,000 core GPU clusters with exabyte scale namespaces sitting behind them. But what a lot of us do is things like fine-tuning and inferencing. So we see this across industry all the time, whether it's medical, regulated industries like financial services, retail customers coming in and taking these models that have been produced by these kind of frontier companies and then bringing their own data against them to fine-tune them and create specialized models for math, for science, for a number of different purposes that are out there today. And then if they want to carry that forward, they can also do inferencing on top of those, bring in capabilities like RAG, store your unstructured data in something like blob storage or in S3, GCS, and then be able to augment your responses along the way. So really this breaks down into kind of two paths for us from a storage requirements perspective. So first is those AI training customers that are out there. So they are bringing a massive amount of raw training data to Azure. We're talking petabyte to exabyte scale. As customers are bringing these things through, they're running them through their pipelines. And that's just data that exists today. We also see more and more of these kind of frontier models training on synthetic data. So, we've kind of produced all the data we can in the world. So now they start to produce synthetic data. You see things like maybe like DeepSeek and some of the distillation methodologies that they're using to drive that up. So we only see that data going up for what's coming in for raw data, and then ultimately the size of those cleansed data sets is growing as well. That leads to larger checkpoints, ultimately as we kind of go down the chain. When it comes to kind of customers that are doing the training and fine-tuning side of things, we find that they still use the regular capabilities in our platform. So they take advantage of things like lifecycle management. They take advantage of data security in the platform. It turns out it's kind of back to information architecture constructs, and we still talk about data lineage and being able to track those things through. Once we get to the inference side of the house, then we're really talking about distributing our models, where are we going to place them, how can we get model load times up, and then often we're doing things like versioning our models and tracking inputs and outputs across those. And with that, I'll turn it over to Daniel to talk about RAG.
Thanks, Scott. Yeah, RAG. We have already seen a slide today at a keynote about retrieval augmented generation. That's what I want to talk with you and how we're doing this on Azure Storage. But what's the question behind? So the question is, how do I bring my domain knowledge and my domain data to an LLM? And I have an easy answer for you. Just train an LLM. Well, the first and is mostly not the smartest answer. Yeah, it will cost you a lot of money, millions of dollars. And on the other hand side, you will waste a lot of time. So let's have a look on 3 other options, how to bring your domain knowledge to LLMs. The first one is prompt engineering, so in-context learning. So maybe you have seen it when you go to chat.com, the web interface of ChatGPT. You enter your prompt and you can upload data. So I can upload PDFs, I can upload images, and then I can prompt. So what I would do, I upload my specs I've written, release notes of our tool sets, and I write the prompt. Hey, ChatGPT, create me an overview, a table that I can show to my manager what I've done the last 6 months. And I'm smart, I'm handing over this prompt to Scott. And Scott is typing this prompt in, and ChatGPT says, oh, yeah, I know Daniel, but he must be on vacation the last 6 months because I've never heard about anything about him. So that's fine for you, but it's not good for a huge organization or you want to bring this domain knowledge to a broader audience. Yeah. So second method could be fine-tuning. Yeah. So it's way cheaper than training your own local language model. It's more like learn new skills. Yeah. But when we're talking about domain knowledge, that is subject to change. Yeah. So coming back to my documents, there's version 1, version 2, version 3. So in the end, fine-tuning is not good for frequently changed data. If you want to bring in more domain knowledge, yeah, so for your industry and so on, it's perfect. Yeah, put in such kind of data which, extends your base knowledge. And the third one is RAG in the end. So we want to learn new facts, and this should be automated. It should combine both worlds, prompt engineering and fine-tuning. So how does this look like? So combine reasoning and knowledge. So it's an external knowledge, and the best thing should be, it should be orchestrated. I don't want to take care about this. Everything should be automated. I just want to prompt in and get my response back. On the right-hand side, you see, in the end, it's just the UX you have. Could be an app, could be just your web interface, which points to an app server, or call it orchestrator. And the first query will not go to the LLM, it will go to the retrieval system. It will query the knowledge we have created. And with this knowledge, we combine with the prompt I gave to form the context window of the LLM to get the response. And for this, we can have different data sources. You can see it here on the right. There could be just blob storage. There could be a SQL database, no SQL databases, and so on, depending on your rack system you want to have. So how does such kind of rack pipeline look like from a storage-centric view? We said we want to make everything automated. Mostly these are 3 main pillars. First, it's data ingestion and preparation. Yeah, of course, we need our domain knowledge. Yeah. And the second one is how we store this domain knowledge in an efficient way. And the third one is, of course, the retrieval and response. I want to get something back with the data I brought in this pipeline. So starting from the left, we're just ingesting raw data. And raw data, that can be massive. And for cost regions and so on, it makes definitely sense to clean the data. Just filter out the relevant data. And then we are chunking the data because we cannot bring all these data, this can be gigabytes, petabytes of data, to the context window of the LLM. So we are chunking this data. So think about a PDF, we have a reader, we're maybe transfer this as a markdown, and then we're creating chunks out of this. These chunks should be, in the best case, overlapping. Why? Otherwise, we would lose context. Think about different heading lines, and we have just the snippets in between. We lose context. So that's one best practices on data chunking. And with these chunks, in the end, for us storage geeks, they're just blobs, single text files, millions, billions of text files in an object storage. And then with RAG, vector DBs become very popular. There are a lot of out there, like open source, popular one, Pinecone as example. And we are generating these embeddings and store it in the vector DB. Later on, I can talk a little bit more about Azure AI Search with a vector DB, what capabilities we have from a search perspective. And that's mostly it, because then we're coming back. The data will be fetched from the vector DB, combined with my prompt, feed it into an LLM, and I get the response back. So our enterprise customers have different requirements on this. The first requirement here, on the left-hand side on the bottom, of course, to bring their enterprise domain-specific data to the foundation model. But more important is low latency access to the model and to the data. Maybe you have played around with LLMs and downloaded some on your local laptop and started it and started prompting and you see 2 tokens per second, 3 tokens per second. This takes long. In the end, we need a high-performant infrastructure from a storage perspective to get low latency access out of there. We don't want to wait, and even we don't want to have a slower LLM when we feed it with data on rack. The third requirement is, of course, the integration with VectorDB functionality. As said, I talk a little bit later on Azure AI Search, our VectorDB as a service. The next requirement, and that's really important because it's often forgotten. It's timely data and index updates. This data is changing. Think about my spec I wrote, I delete something, I create a new version. Scott is still reading the old version, getting out of the LLM, yeah? Or I made a mistake and I deleted it, and it's still available on the LLM. So that's really important. And thinking about this, that should not be a manual process. It should be automated in the best way. Yeah? And last but not least, security and access control. That's mostly not only security on LLM. Yeah? There are a lot of new vulnerabilities upcoming, how to jailbreak and so on, prompting, injections. It's as well how the data is secured, because our rack data is stored in Azure Storage, and here we have different capabilities to secure your data. So these 5 requirements can be fulfilled with Azure Storage, like multi-protocol access. Scott talked about this before. In the end, it's unified storage for heterogeneous updates. It's a super hard word for a German native, but in the end, we want to bring our structured and unstructured data to the object storage, yeah? And this is mostly done via a REST API, yeah? But not all systems can talk REST, yeah? So remembering I'm responsible for AC copy, that's a command line tool, so a lot of our customers are bringing data to the cloud using AC copy, just uploading data or pulling data in from different cloud providers. Legacy applications, ERP systems could use SFTP, or you can use NFS on a Linux machine, just mount it and do an rsync to copy the data in. Yeah, our answer to low latency access is premium block storage. I have a slide on this later on as well. VectorDB integration, as mentioned, we have an as a service offering Azure AI Search. Azure AI Search supports multiple indexes, and it's dev-focused. So if you want to write Python, you're welcome. We have a Python storage SDK and as well connectors to Azure AI Search. Yeah. And with Azure AI Search, you're not limited only to vector. You could as well do keyword-based search or combine it. That's called hybrid search. Yeah. Or do on top semantic ranking. So that's up to you, and that's a little bit depending on the data itself. Yeah, there is no, in general, answer on this. Another important bullet point, and I talked on this, it's the freshness of the data, and I want to have this automatically. And we have 2 features integrated in Azure Storage. The one is the blob change feed, and the other one is change notification. So with blob change feed, we are writing out Apache Avro files. Could be another blob storage, and your application can run, I don't know, every 24 hours, every 12 hours, pick up the changes and apply them. If you wanted more near real time, you can use change notification. So like these are firing up events, and you can subscribe on these events. And a good example would be subscribing on a serverless Azure function, and then when I have deleted my document, it will be removed from the index. Just looking, we have 5 minutes left. And security, yeah, when you're working with Azure, our identity as a service is Azure Entra ID, former known Azure Active Directory. So we are very good in changing names. And we have role-based access control and attribute access control to secure your data. I know where this looks like more like a sales slide, yeah, but I don't want it to remove it because it's important to understand. We did some tests on premium blob storage, and while our standard blob storage running on spinning disk, we achieve a really, really high throughput, yeah, It's not only from an IOPS perspective, as well on the other hand side, ingress and egress, but for AI workload in combination with RAG, our test figured out that premium block storage is around about 2 to 3x faster, depending on the operation you will hit on the API. So it's tested from a latency with 400 KB PDFs. And in the end, you're saving 95% on transactions. And cost saving, especially in the area of AI, is always welcome. This is my last slide. Yeah. As mentioned, so think about a storage cluster. We have 10 racks, we have 20 racks of spinning disk. Yeah, and even if we can say, thank you, even if we can reach terabits of throughput, there will be the point where we are limited from the hardware. Yeah? And that's why we increased a system called scaled accounts. So we can horizontal scale out on clusters. Yeah? So we call it home stamp. So that's the landing cluster. When you create a storage account, it will be bound to a single hardware. And then we can add multiple hardware stamps and horizontal scale out. In the end, in front is an Azure Traffic Manager. That's a DNS-based load balancing, which allows us, to fine granularly adjust weights from the request perspective. And this eliminates the need for customers to share the data across accounts, because that's what we have seen in the past, that customers with a huge demand on IOPS and bandwidth sharded or built their own sharding technology on Azure, and we want to avoid this. And the cool thing is, again, the pricing, it's no new product or new SKU. It's in the end auto scale, and you pay the same if you have just a single hardware. Having said this, giving back to Scott.
Okay, cool. Thanks, Daniel. So just kind of wrapping up and key takeaways. So is object storage viable for AI training workloads? Absolutely. It's kind of required given the size of these raw data sets. We're beyond the days of talking about terabytes, and now we talk about petabytes, often hundreds of them, to exabyte scale. And these are going to continue to hockey stick up and be multi-exabyte namespaces at some point in time. So you've got to think about object storage as a backing platform there, picking a platform that's going to be performant for you, so it's going to meet your throughput and IOPS demands, and then potentially have access to all your various compute sources where you might be doing any of that data cleansing, data preparation, things like that. So in our world, that's our kind of multi-protocol access strategy. If you're looking at the other hyperscalers, maybe you're looking at Amazon S3, or you're looking at Google Cloud Storage, maybe you're looking at things like traditional file system drivers and leveraging Fuse or things like that on top of Linux to be able to get access to those just through kind of familiar interfaces. And then on the RAG side of the house, a couple of things you want to think about for sure. Identity is very important. I don't know if anybody here is a Microsoft 365 customer, maybe use Google Workspace, things like that. Congratulations, you're all part of these massive RAG workloads that are out there and running, whether it's Google, augmenting responses based on maybe your information in Gmail through Gemini, or Microsoft doing it with Copilot along the way. So you want to make sure that these systems are security trimmed, they understand security context of those users. If you are doing large-scale RAG applications, latency does tend to become a thing for you. It can slow down the responses, and perception is reality for our users. They don't like to wait tens of seconds if you can get it done in kind of single-digit seconds and put things in front of them. So with that, I think we're right at time. But if anybody's got any questions, feel free to ask. Daniel and I will be around the rest of the conference, so you can catch us in the hallway as well.
We probably got time for maybe one or two questions if somebody has a question. Got one over here, and then we'll come back to you.
Regarding the checkpoints, how often if you can share the data, how often are they actually used? Or are they just, we're paying a lot for insurance that never gets claimed?
It's experimentation plus insurance. So there's a couple things. Like, I don't know how many of you are out there like buying, tens to thousands of GPUs, but they don't have the best track record. Like, you bring these things in, the failure rates are quite high. So we find that, being able to capture checkpoints at multiple times during the process, whether that's generating checkpoint in GPU, being able to push it off to maybe some type of local disk like HDD or SSD ephemerally, and then we can eventually pull it off there and get it back to object storage. It's very much a time is money kind of situation. So anytime that you're flushing checkpoints, your GPUs are idle, and anytime that you're rehydrating checkpoints, your GPUs are idle. And at the scale and number of GPUs these customers are running, it's not like tens of dollars, it's hundreds of thousands to millions of dollars of lost time, and just measured in minutes. So it's a little bit of an if one, but not a lot of people are training these big frontier models either. We're often consumers of them, and then we're building applications on top of them.
Okay, I think there was one more in the back. We just got time for one more, and you can catch them in the hall, I guess.
No problem. So on the premium blob storage, are you attempting to do any cached hybrid architectures there?
The question was on premium blob, do we intend to do any caching, things like that. So we do some caching internally in our system. Internal implementation details, we don't bring those out. We also have the intent to introduce more client capabilities and client cache capabilities. So today we have an Azure Container Storage offering, Azure Container Storage or AC Store, that has a distributed caching component built into it, built on top of OBJ cache. We also have a Fuse client that I mentioned, Blob Fuse. Over the next couple months to a year, our intent is to also instrument and build a distributed cache into our Fuse client. So, the intent would be we would take a customer with a 10,000 node, whatever. They can run Blob Fuse on all 10,000 nodes, and maybe they want to use 100 of those nodes or 1,000 of those nodes as some kind of read-through cache to have that capability there. So it's kind of hit or miss. It evolves fast, and you just got to kind of figure it out based on your needs.
Okay, thank you very much. I see we've got the time's up sign here. So.